Many people assume artificial intelligence is a search for one master algorithm, an ultimate equation that, once solved, yields perfect understanding. To understand what we are actually building, we must define the theoretical ceiling of computation itself. In 1936, Alan Turing defined computation as a strictly rule-governed, finite procedure. Turing's analysis proved that any mechanized set of rules inherently possesses a boundary it cannot cross. Mathematical logic dictates there will always be problems that a closed system cannot solve from within. This is known as relative uncomputability. If intelligence requires open-ended understanding, it cannot be exhausted by a single, closed, finitely specifiable rule set. Rules dictate execution, but they do not evaluate or revise themselves. Searching for a final master algorithm is theoretically impossible. Intelligence is an ongoing structural process, distinct from a static mathematical solution. The alternative to a closed algorithm is a layered, dynamic progression. In complexity theory, this progression is called step mechanization. Whenever a lower-level task is formalized into strict rules, the higher-level work of evaluating and revising those rules is simply displaced upward to a new layer. The formal mathematical model for this vertical stack is the Turing jump hierarchy. A base layer has a canonical, uncomputable boundary known as A'. A successful jump to a stronger computational layer below that boundary is defined as layer B. Each successful jump mechanizes what was previously impossible at the lower level, while instantly generating a brand new boundary of relative uncomputability above it. This infinite stack works in theoretical mathematics. Physical engineering, however, is strictly bound by space, energy, and time. Intelligence is a limiting process of continuous layer building. Our hardware architecture must be designed to support an open-ended ascent. We have to map this theoretical infinite ascent onto physical reality. How is an endless sequence actually computed? The bridge between unconstrained Turing machines and feasible computation is the polynomial hierarchy. We achieve practical scale through staged bounded ascent. Infinite theoretical limits compress into a finite, nested ladder of verifiable steps. At each rung of this ladder, systems engage in bounded verification games. One node proposes a solution, a second challenges it, a third repairs it, and a final node verifies it. These cycles operate strictly within the bounded parameters of polynomial time, making previously impossible search tasks highly structured and solvable. Modern artificial intelligence relies on this exact challenge and reply structure to navigate hard spaces. Running these layered verification games requires an enormous, compounding volume of raw mathematical operations. Bounded verification makes intelligence mathematically feasible, but it transfers the bottleneck entirely from theoretical mathematics to physical execution. Running these bounded verification games at scale requires massive physical exertion and heat generation in real data centers. Artificial intelligence development is governed by scaling laws, predictable mathematical relationships showing how model loss decreases as you inject more data and compute. There is a critical distinction between logical compute, the abstract mathematical operations required by the model, and the physical resource burden, the actual time, electricity, and silicon required to perform those operations. Classical scaling laws abstract away realization details, hiding the true cost of the physical resource burden behind the clean mathematics of logical compute. This chart shows the excess loss over calendar time for several annual efficiency doubling rates. The black curve, representing a scenario with no efficiency doublings, rapidly steepens downward over time. A flattening loss curve is an escalating operational and energy burden. It represents the physical penalty of attempting to scale logical compute without improving how that compute is delivered. To avoid this penalty, systems rely on relentless efficiency doublings. Increasing the annual efficiency doubling rate alters the trajectory of the loss, buying the system more runway. These doublings are achieved through software-side innovations, sparsity algorithms, tighter quantization, and improved routing behavior. Without these constant stack improvements, the physical burden of supplying logical compute would cause the entire scaling process to collapse. Diminishing returns transform AI development into a brutal efficiency game, where hardware and software must continually renegotiate the real-world cost of computation. These massive physical scaling constraints eventually compress down to the microscopic level of silicon architecture. Modern chip design is a zero-sum resource allocation problem governed by strict physical limits on the die. The modernized version of Amdahl's law represents the tension on this die. Space is split between specialized fixed-function logic and general programmable compute. To determine how to divide this space, engineers calculate the value-scalable fraction of an AI workload. This is the specific portion of computation where adding more effort continues to improve the actual output quality. Because of the relentless software efficiency doublings we just explored, the value-scalable fraction of AI workloads is constantly growing. This creates a collapse threshold. As the value-scalable fraction grows, the mathematical justification for dedicating silicon to specialized fixed-function hardware drops to zero. Hardwiring an algorithm into silicon becomes a liability if software evolution quickly moves the frontier of useful computation to a different method entirely. Over-customization in AI hardware is a trap. Chips must prioritize a highly flexible substrate to capture the constantly shifting, software-driven gains of the value-scalable fraction. Modern silicon design has moved past the generic flexibility of the CPU era. This is AI programmability. It is a shared, software-mediated substrate specifically designed to absorb model evolution. This specific type of programmability allows a single hardware generation to absorb continuous efficiency doublings without needing to be physically redesigned and replaced. This brings us back to the core tension of machine intelligence, mapping infinite mathematical boundaries onto finite physics. The modern hardware stack is the physical realization of the theoretical limiting process. It is a foundation built not just to solve one closed equation, but to survive an endless, ongoing climb.